Also, the chat box will be enabled towards the end of the talk. And if you have questions, they can be typed into the chat box and be seen by all participants, and they will be answered in turn. So my name is Ian Sanders. I'm in Dublin, Ireland, and I welcome you to this Zoom event. It's the third in the series of lectures to commemorate the life and work of Ed Scott, who died in 2021. It's my pleasure to introduce our speaker, Dr. Audrey Bouvier, who is a professor in the University of Bayreuth in Germany. Her title, as you can see on the screen, is Achondrite Meteorites, Messengers of Early Planetary Accretion and Evolution. With her expertise in petrology and isotope chronology, she is very well placed to understand the processes of accretion and melting. Audrey told me earlier that the remarkable achondrite Erg-Chech 002 will feature in her presentation. This meteorite, Erg-Chech 002, is made of andesite, and it was discovered in the spring of 2020. In less than a year, it was the focus of a remarkable PNAS paper, which showed in particular that it crystallized long before any other achondrite, and at the same time as chondrules were being made. That Erg-Chech paper was not accessible to me through the University Library in Dublin. And it was Ed Scott who came to the rescue, and he sent me the paper by email as a PDF. And it arrived well marked in yellow highlighting and comments, reflecting Ed's curiosity. That email turned out to be one of my last emails from Ed, and he would have been delighted to know that Erg-Chech would feature in this tribute to his memory. So without further ado, I hand you over to Audrey.
Well, thank you very much, Ian, for the nice introduction and for the invitation, and for everyone to connect today or tonight. It's a great honor to speak today about some of the work, I hope, related to Ed's research, broader research on achondrites. He worked on a lot of topics, and I thought it could be a good selection. So before starting, I would also like to thank a lot my students and collaborators with whom I've been working on this project related to achondrites over the last few years, and a lot of their contributions will be in the talk. Okay, so I hope today I can go over some topics, general topics about achondrites, so differentiated meteorites, and how we can use them actually to trace the very early disk evolution, so the first stages of disk, protoplanetary disk, and the differentiation on planetesimals. And trying to go from this to looking at differentiation, but also to try to constrain accretion ages of planetesimals and the applications also for short-lived radionuclides. So in the last part, I hope I will also cover rapidly some dynamical evolution of planetesimals, what we can learn actually from differentiated meteorites. So all of you probably know by now that we have more than 74,000 meteorites in the Meteorite Bulletin database, which is a great source of resources for the composition of meteorites, and especially all the latest classifications. There are more than 2,000 a year now. But we also have the great chance to have 3 asteroid sample return missions now from chondritic planetesimals, asteroids, which are near Earth objects. So we can sample now quite a lot of potential parent bodies. I will go over that. But from all the 1 to 2 million asteroids, at least I think that have more than 1 kilometer in diameter, but also Moon and Mars, we can sample about 10% of this from achondrites. So let's take a look at the basic classification of meteorites. So of course, we want to look either at the early stages of planetary evolution, of the molecular cloud evolution. We will look at the chondritic materials, which are unmelted chondrites and undifferentiated planetary bodies, at least the parts of the bodies that haven't been melted, looking at astatite, ordinary, or carbonaceous chondrites as the main groups. And those represent today 90% of the finds that we have recovered. When we want to look at the achondrites, we're getting limited in the amount of materials we have, and we have about 10% of differentiated meteorites that come from planetesimals that are differentiated with a core mantle increase. Depending on which reservoir layers into those planetesimals we want to investigate to understand, we can look at different types of achondrites. So either the silicate-rich, the stony achondrites from asteroids or Moon or Mars. I will focus today on discussing asteroidal achondrites, but we can also look, of course, at the iron meteorites, so the metal cores, metal sulfur-rich cores of planetesimals, and finally the stony iron meteorites, which can be a mixture of silicate or olivine and pyroxene embedded into a metal, which could represent the core mantle layers, but also probably a potential mixing due to the planetary impact. So going from that, I think Ed had a really nice paper in 2015 summarizing the chronology of differentiated meteorites and chondrites. And we can see here on the left side in this figure that the differentiated meteorites formed early. So if we look at here the start of the solar system about 45, 68 million years ago, we can see that the iron meteorites will be amongst the oldest ones. Those are hafnium tungsten ages that provided the very early evidence of planetary differentiation and core mantle differentiation. So they're basically dating the metal and silicate segregation. And from that, we can see that also we have the basaltic achondrites from an ungrouped eukaryote, for instance, Azuka 881394, which will be the earliest ever dated achondrite at that time, although there's been some changes recently with the ages due to uranium isotopic composition. But we can see that those formed within the first 3 to 5 million years. We have formation of eukritiec to uralite, angrite, or aurite meteorites. So those we think accreted early with ages within 1 to 2 million years for the planetesimals to accrete. Compared to the chondrites, they formed earlier than the earliest ordinary or carbonaceous chondrite, and the CB chondrites forming a bit later, 4 to 5 million years after CEIs. So those accretion ages for chondrites are nicely constrained by the age of chondrules. If we take the latest age of chondrules, we can have an estimate of the accretion age of the parent body. So for the achondrites, it's a bit more complicated because we're measuring crystallization ages for ions or for basaltic achondrites. So for those, we have to estimate the accretion time of the planetesimals by doing some modeling, thermomodeling, modeling, geochemical modeling based on the fractionation of the elemental ratios, for instance, for those meteorites. So we have a lot of uncertainties, especially with the basaltic achondrites, to try to estimate their accretion time, which could vary from 0 to 2 million years for most of the planetesimals related to angrites, eukaryotes, or uralites. We also want to start comparing the inner solar system and the outer solar system from the non-carbonaceous or carbonaceous chondrites. I'll come back to that. But what we can see again is that in both regions, the chondrites accreted late, and in both regions, probably the achondrites accreted early, but we would like to have more precision on that. So going on from this, the achondrites are, I think, the best tracers that we can have for the earliest stages of the protoplanetary disk. If we want to look at the first 1 to 2 million years maximum after the formation of the calcium aluminum rich inclusions, we want to look first at the differentiated planetesimals, because those formed early, they probably had more aluminum-26 as a short-lived radionuclide, so as a source of radiogenic heating. So the radioactive decay of aluminum-26 to magnesium-26 with a half-life of about 0.7 million years provided a lot of heat at the beginning of the accretion and differentiation of the planetesimals. So after 1.5 million years, probably the chondrites started accreting aluminum-26 was much lower in abundance, and hence didn't reach a melting stage or mammoth ocean stage. So what are we looking at during the planetary differentiation? We're actually interested to understand the stages of planetary melting. So first, when the planetesimals finally reached the melting point of the solidus for iron nickel sulfide, where we start segregating metal by percolation into the planetesimal forming the core. If the aluminum-26 is present in a high abundance, we can continue heating the planetesimal until we reach silicate melting, and finally sulfide segregation can occur, and we might reach a magma ocean stage if there's enough heating. So those are the also important processes that we can look at by looking at the different types of meteorites and differentiated meteorites, but also the systems we're using to trace not only the chronology, but also the isotopic variations of those reservoirs that are formed. So another aspect that has been really important over the last years is to find this early dichotomy nucleosynthetic anomalies. So both for achondrites and chondrites. So first it was established for chondrites, but as we looked at achondrites, they actually sample more planetesimals, and like I said, they're sampling very early planetesimals. So this dichotomy, the separation of two nucleosynthetic reservoirs, for most of the elements we've been measuring, was actually established within the first 1 to 2 million years after sea ice, and has been assumed to be associated with the formation of Jupiter, possibly, or other possibilities are pressure maximum in a disk that have been proposed. So if we look at the non-carbonaceous meteorites here in red, or the carbonaceous chondrite meteorites in blue here, this separation is observed for both lithophile elements that are actually tracing the main accretion stage of the planetesimals and planets. But also we find it for siderophile elements that can be added to the planets after core formation. So those are going to also trace the late accretion stage and potential materials added to the planets. So if we look at the Earth, actually, the pre-late accretion Earth was above plus 0.2 epsilon values for ruthenium, for instance. And we could actually trace the outer solar system possibilities of outer solar system materials being added late. Okay. But in all these diagrams, the Earth and the Moon are very similar to ancestral chondrites with a value of 0 here for all those mass-independent variations. And also the Earth and the Moon look like they are often at the end of the trends. Okay? So this is important also when we assess the formation of the Earth, potential building blocks and so on. So of course, we wonder where the sea ice or the sun could be, but sea ice are way off the charts and would be added in various amounts in the carbonaceous chondrites. So now we can take a step back and look again at the classification of the meteorites and try to actually divide them into non-carbonaceous and carbonaceous chondrites and achondrites. And we can see that most of those meteorites, actually the groups that we have now, can be either from differentiated meteorites as privative achondrites, but also differentiated meteorites in both the NC and CC groups, with a more limited sampling in both of those cases from differentiated planetesimals from the carbonaceous region. So we have here the tafasacet-like meteorites are actually the only grouplets of meteorites in the CC group. And we have several groups of ions and palazites as well in the CC reservoir. So despite the limited abundance, when we want to compare NC and CC achondrites, we have also a lot of ungrouped chondrites, but also 150 ungrouped achondrites now in the classification, and about 150 ungrouped ions as well that could potentially sample other planetesimals. So those are going to be important to complete a view of the sampling we have today of meteorites and how many parent bodies we can sample. And right now, from oxygen isotopic studies and nucleosynthetic anomalies, we could estimate maybe 150 parent bodies being sampled. Okay, so taking this, we can try to start looking at differentiation ages, but also accretion ages, and how to constrain this. So those are nice, actually, compilations of data for carbonaceous and non-carbonaceous ions, chondrites and achondrites, with our nucleosynthetic anomalies showing again the dichotomy, like here for molybdenum isotopes, and trying to compare the accretion time of their parent bodies. So most of those accretion ages were actually from the paper by Sugura and Fujiya in 2014, where they estimated the time of accretion and compared it here with the chromium isotopic anomalies in 54 chromium. So this was important because we can actually start comparing again the time of accretion of ions that look like they could be earlier in the NC region compared to the CC region. And as I said, we have a limited sampling in the outer solar system with tafasa set here for the achondrites, so primitive achondrites at least, and the chondrites much later in the CC region and the NC region. So for the chromium isotopic evolution was maybe a correlation was suggested maybe that could be correlated to adding some materials enriched in 54 chromium over time to explain the trend that we see from the NC to the CC chondrite. But tafasa set and the grouplet of NWA011, this basaltic achondrite grouplet, were of the charts, at least for the correlation, at least for chromium isotopic anomalies in time. Of course, now we could suggest or wonder if those accretion times are actually correct, or could they be affected by a lot of physical parameters in the CC region? For instance, the porosity, the water content in the planetesimals could affect the models. But also, even for chromium, we could wonder if we just had two reservoirs, isolated reservoir, the NC and CC. So what we need is more thermochronological constraints on those planetesimals to try to better assess at least their accretion time. So this is something that is regularly done in terrestrial chronology, at least. We call this thermochronology for using different isotopic systems and mostly long-lived for terrestrial studies, but for cosmochemistry, we can also use short-lived radiometric systems. And we have a whole range of systems we can use, and basically, depending on the systems we're looking at and the mineral we're going to use, we have different closure temperatures of those systems. So for instance, in terrestrial studies, we will look at uranium, lead, and zircons as the system closing at the highest temperature. We might look at uranium, lead, and clinopyroxene, for instance, in meteorites. But we can see that systems like uranium, lead, and phosphates like apatite causes a much lower temperature, about 500 degrees here, compared to zircons. And then potassium argon, for instance, in feldspar is at even lower temperature. So this has also been deduced from experimental data and diffusion data of elements. Those are the daughter product of several systems, such as aluminium magnesium, so magnesium and anortide and feldspars, chromium and olivine from the manganese chromium system, or for lead diffusion in clinopyroxene, orthopyroxene, but also phosphates. We can see that we have diffusion rates that are even very slow to very fast or faster, depending on the temperature range, also the cooling rate or the grain size. So those can all be taken into consideration when we do also our modeling. So we decided to do this on tafasa set, and we actually used, this was done by one of my students, Nima. We looked at tafasa set and different meteorites that we call tafasites, although it's not an approved name, but we looked at a grouplet of several meteorites that were classified as CR6 or 7 in the database that are related to the CR chondrites. At least that's what we thought at that time, but it's actually related to tafasa set. And we proposed a new group, and the first group of carbonaceous chondrite, primitive chondrites, formed in the outer solar system. So we looked at the uranium lead phosphate ages, and we modeled those against the manganese chromium and hafnium tungsten ages that were published for tafasa set. And we could deduce a nice thermal modeling that was done by Vladimir Newman in Berlin, and that took a really nice scope of data that we had to actually fit those data into a profile of cooling for the parent body of tafasa set. So from this, we can deduce that the parent body probably formed at 1.1 million years after CIS, and probably was pretty big to sustain heating over 10 million years. And although tafasa set uranium lead age could show a later disturbance, so there was potential additional disturbance or heating that was also observed. So a radius of about 100 kilometers for the parent body of tafasa set and other meteorites related to to it. So from that, we propose that tapas asset actually probably its parent body formed at a time very similar to the Acapulco-Rites or uralites in non-carbonaceous region, which are here in red. So of course, when we look at the achondrites now, we know that most of the achondrites, besides from Moon and Mars, are either HED meteorites from Vesta or the Vestoids parent bodies. Those have seen a lot of thermal effect and metamorphic effects, so often we do not or form too late to be used for aluminium magnesium or an association at least with the two systems, aluminium magnesium and uranium lead. So we turn over to look at the Achondrites. Achondrites are the minor group of meteorites that are early formed with very early ages of crystallization. Obrites, brachinite, winonite, or Acapulco-Iloranum brachinites. So once we go from some differentiated meteorites to primitive achondrites, it's much more difficult to obtain different ages from different systems and to make sure we're actually dating the same event, but also their composition is often not suitable for high precision dating. So we have also about 3% now of those ungrouped achondrites, and that's a unique opportunity to look at other planetesimals. So what do we do when we actually go in the lab to get these radiometric ages? We can look at different mass spectrometers that we can use to get high precision isotopic ratios by magnetic sector mass spectrometry. So we have two ways of doing this. We can either take a meteorite and do some mineral separation to get mineral isochrons. For this, we have to go through the dissolution stages and a lot of ion exchange chemistry to finally analyze our elements or purified elements, either on multi-collector ICP-MS or MC-ICP-MS or thermoionization mass spectrometer like here to get the high precision ratios. Alternatively, we can also use in situ methods such as secondary ion mass spectrometry, such as here, shown here, the chemical 80HR, where we can actually obtain single spot analysis for systems such as aluminium magnesium, manganese chromium, or uranium lead ages of uranium rich minerals such as phosphates or foliochs, zircons, padallites, for instance. Okay, so for short-lived radioactivities, we have a lot of systems that have been discovered in meteorites, and the most common ones that I'm going to discuss, at least here in the talk, is aluminium magnesium dating with a half-life of 0.7 million years, but also manganese chromium 3.7, hafnium tungsten 8.9, and the curium uranium decay is actually important for uranium isotopic ratios and has a half-life of almost 16 million years. And I will also discuss at the end the samarium neodymium short-lived system with a half-life of 103 million years. So what do? We actually measure the decay product. So for aluminium magnesium, we measure the mass-independent variations here in magnesium-26. And if there's a nice correlation with the aluminium magnesium ratio, so the parent-daughter ratio, the slope of this isochron or correlation here gives us the initial abundance of the parent isotope here, aluminium-26. So the slope here gives us a ratio of about 5×10 to the minus 5 for the CEI. This is close to the canonical value of 5.2 10 to the minus 5 for CEIs and for the solar system. So the aluminium-26 is very important because it was formed shortly before injection into the solar system due to this very short half-life. And if we can use it as a chronometer, if it's homogeneously distributed throughout the protoplanetary disk, we could get ages of meteorites down to 30,000 years precision. So it's extremely powerful for this. And it's also this important source of radiogenic heat for differentiating planetesimals. So we're really interested to constrain its initial abundance. So the first group of meteorites that we've been focusing on in the literature is the Achondrites. So the Achondrites are extremely interesting because they have different petrogenetic groups. So we have the quenched Achondrites, which are basaltic meteorites, and have formed very early after CEIs, so within 1 to potentially 4 million years after CEIs, we had the formation of the quenched Achondrites. And we have plutonic ones, so coarse-grained anhydrites that formed later, down to almost 11 million years after the first quenched anhydrites. So we have a long recording of magmatism on the anhydrite parent body. But we also have some breccias in between that have been identified with a group of 2999 or Northwest Africa 6291, which have ages of about 45, 60 million years in between. So there are some intermediate age breccias, and something that has been really important is that we had to measure the uranium isotopic composition to actually correct the lead ages of all the anhydrites. And there were differences found, identified by Tissot et al., for instance, between the quenched and plutonic anhydrites just caused by crystallization. So those were stable fractionation effect. So also something that is really important is that most of the anhydrites are so precious and small and depleted that often we have to measure the uranium isotopic composition on the whole rock, not necessarily the pyroxene that are dated for lead. So this could cause also some issues. And I'll go back to that later. Some high precision work also, I've been trying to actually estimate the initial abundance of aluminum-26 for anhydrites and find some discrepancies with other meteorites and with the ages of CAS, for instance. So if we actually, depending on the age of the formation of the solar system, we could try to estimate the abundance of aluminum-26, and some authors suggested that the anhydrites formed actually in a region that was depleted in aluminum-26, only 25% of the canonical abundance. So this is important because, again, when we model the planetary differentiation and the heating of the anhydrite parent body will have to form within 0.2 million years after CAIs to reach a melting temperature. So this influences also the accretion ages of the anhydrite parent body. So going on with the anhydrites recently, some work based on experimental petrology constraints for partial melting, or at least for trying to track and model the source of the different groups of quenched anhydrites. It was suggested that the anhydrite parent body should be extremely large, maybe 3 times the size of a star at least, to explain the magmatic differentiation of the 2 groups of quenched anhydrites. So this was a paper a couple of years ago by Tissot et al. And last year also some high precision measurements of oxygen isotopes in Seagull grain xenocrest that were found in the anhydrites indicated that potentially some parts of the anhydrites was actually mixed by impact. So a large impact event which would have contributed to the formation of the anhydrite parent body, mixing some different sources of materials. So this would also affect potentially our chronometers if there was secondary disturbances due to impact and mixing. So going on from that, a great chance in 2020 was to actually found, as Jan has mentioned earlier, the Church 002 Achondrites, which is ungrouped. It was found in Algeria, and the great chance is that it's also more than 45 kilograms of material that was recovered extremely rapidly, providing sample to a lot of labs. So it makes it very affordable, accessible, at least for measurements. And the other very interesting and particular advantageous mineralogy of Church makes it very favorable for a lot of radiometric systems. So it's a planetary andesite, sorry. So andesite not as on the Earth, where we could think about subduction zones. Sorry, but andesitic because it's enriched in alkaline elements. So Church 002 is here, and it looks like a partial melt from an ordinary chondrite source. So it's similar in some composition with other ungrouped chondrite, but very different, for instance, from NWA 11119 or the eucrates here now, completely basaltic and not alkaline at all. So when we looked at Church 002, it appears to be a non-carbonaceous achondrite. So it's ungrouped, it's unique, but we can try to associate it with other achondrites that we know very well. So when the oxygen isotopic composition, for instance, the big delta O17, 54 chromium anomalies, indicate, at least here, all the red points, that church is within the field of anomalous eucrite, but at least related to anomalous eucrite, and distinguished from Vesta. It's also distinguished from Angrite, so Barkinite, for instance. And the early work by Barra et al., which was the first report for the chronology, was done by in situ SIMS analysis of feldspars, showed a very high abundance of aluminum-26, 5.7 10 to the minus 6, the highest for any differentiated meteorite that was so far measured, with a time after CEIs corrected for the half-life about 2.3 million years after CEIs for its crystallization. So they could model a fractionation from a chondritic source within 1 million years after CEIs. Something that was also interesting was to look at the diffusion of iron and magnesium in pyroxene. So this is an autopyroxene xenocrest, and showed very fast cooling rates early on during the crystallization process. So between 1200 and 1000 degrees C. So about 5 degrees per year. So extremely fast cooling. So when we measure the aluminum magnesium by solution now, by doing mineral separation, mineral isochrons, not by in situ method, we have several studies. So last year we published with my student Philippe Reger a study, but there was also Fang et al. Before, and now Connelly et al. Has published. So we have 3 data sets that are consistent at 8.9 10 to the minus 6 for the initial ratio of our church. So this isochron is distinct from the isochron obtained by SIMS, and there's about 0.5 million year age gap between the two methods that were used to date it. So this has been associated maybe potential miscalibration for the sodium-rich pelagioclase that were analyzed by SIMS with a standard that is more calcium-rich. That's a possibility to correct the aluminum-magnesium ratios. But also it could be that by a mineral isochron method, we're actually mixing grains, and maybe we don't have a pure feldspar fraction of analysis. There could also be different feldspar generations, I was told. So this could also be the case that we're just mixing some grains, and the closure temperature we have to assume will be different for the mixtures versus the pure plagioclase. And if we take the closure temperatures of plagioclase versus possible mixtures with pyroxene, for instance, that could be a bit higher. The cooling in that case will be much slower, 200 degrees per million years. So this could be subsequent to crystallization as well. So going forward with the uranium-lead chronology, I mentioned we have to measure the uranium isotopic composition. This has been extremely important since 2010 in the early work by Brenecker et al. That showed that we can have in meteorites also isotopic variation of uranium caused by the decay of 247 curium, producing 235 uranium. But even on Earth, we have large variations in uranium isotopic composition due to partial melting, to redox reaction, low temperature reactions, producing stable isotopic fractionation effect. So all those possible processes have to be taken into consideration even for meteorites. And when we measure the uranium isotopic composition, it's extremely important to have a system that is isotopic equilibrium. What we're measuring for uranium should also be for lead isotopes. This is important to use in the decay equation for radiogenic lead ages. Here, the 207-206 ratio that we use to calculate those ages. We need to use the uranium isotopic composition, which was assumed for a long time to be 137.88 as a common ratio. But now we know, we know that we have to measure the uranium isotopic composition to calculate a time here from this decay equation, okay, in a closed system. So we did this on air church, and we did this on pyroxene. This was the report we had from the most hydrogenic fractions, where we obtained a very old age, crystallization age of 45, 65.9 million years. So this was the age that we reported using the uranium isotopic composition measured on pyroxene. We also measured the bulk rock of Fairchurch and found a higher ratio. And just the difference of those two isotopic ratios actually create an age correction of almost minus 0.6 million years from using the bulk rock value. Okay, so this is the correction we made using the pyroxene composition. And the Fairchurch actually has a uranium isotopic composition that is distinct from all the anhydrides. This is the range of composition found from the quench to the plutonic anhydrides, and Fairchurch is actually different. So we cannot even assume a common isotopic composition for all the differentiated meteorites like we thought before. So the uranium isotopic composition has to be measured, and once we've done that, we can calculate our LLD age. If we use the aluminum magnesium ratio that we measured in the same sample that we had of Fairchurch, and using the aluminum magnesium age gap with CEIs, assuming a canonical value, we can model a T0 4567.8 plus minus 0.4 for the age of the solar system. So we went on and then used also the phosphate ages for Fairchurch, which was younger, 4564.3 million years. We measured the spice sims here, doing single spot analysis in Fairchurch. And we could use this age to actually model and use at least a constraint on the lower temperature closure of the system of lead diffusion in phosphates, about 770 Kelvin. So doing this, we did this for TAFAS asset. We fed the uranium lead data for pyroxene and phosphates in Fairchurch, and we compare this also with the aluminum magnesium ages here in pink and green. We compare this also with the chromium data here, the white triangles, although the manganese chromium ages also differ by 1 million years between two studies here. So we didn't include this in the fit, but we could at least report them on our curve. The argon-argon ages that has been reported in abstract is actually much younger, and we think it's associated with potential impact. This is also something to consider with Fairchurch, okay? But we don't know exactly the extent of that. So when we take into consideration all those chronometers, we can also model again a best fit for the accretion time of Fairchurch, only 0.1 million years after CEIs, and a small planetesimal here, 20 to 30 kilometers in radius for Fairchurch. So since that, there were actually additional studies that also provided more ages for Fairchurch. There were two more uranium lead ages. They're actually slightly differing from the report from Riga et al. So the report from first from Cristianino, for instance, in Nature Communication, was slightly younger. And again, another report by Connelly et al., which is slightly older. So we have now 3 uranium lead, 3 uranium corrected lead ages that slightly differ. And those two actually use the bulk rock uranium isotopic composition that are similar between the two studies, but still they found an age difference of 0.6 plus or minus 0.3 million years between the two studies. So Cristianino actually compiled this to look at the free decay of aluminum-26 with time to try to constrain the initial abundance of aluminum-26. And they found that their report of Fairchurch was consistent with the age of CEIs of 4567.3 million years. The Riga et al. Point is here in blue. The data from Connelly et al. Were not published yet, so that's what they used. And they compare with the anhydrides here as another anchor for aluminum-26 abundance, showing a different line of evolution, so constraining a much older age for the solar system value at 510 to the minus 5 for the canonical CEIs. Okay. So Fairchurch could either indicate large aluminum-26 isotopic heterogeneities in a non-carbonaceous region, or alternatively, there could be variation in the uranium corrected lead age of CEIs or achondrites potentially. So if we take a look at this, we have two possibilities, like I mentioned, 510 to the minus 5, we could have 2 T0, depending on which achondrite we're actually using to constrain the aluminum-26 abundance. So if we redraw this, now we can also compare of course, the aluminum-26 abundances obtained by mineralized isochrones or SIMS. And if we take the 3 studies now that have been reported for Fairchurch here in red, those are the non-carbonaceous meteorites. we can actually compare again with the different CEIs we have for aluminum, magnesium, and uranium lead ages. And now we can use Church 002 as an anchor again, taking the average of the 3 studies, for instance, which is the white diamonds here. And we can obtain a T0, which is about 4567.7 million years, plus or minus 0.2. And if we take the Angrates as anchor again, now the T0 it will be much older. This has been also proposed by 2 papers last year by Tesh et al. And Pirala et al., questioning the age of formation of solar system independently from CEIs just by using the Achondrite systematics for uranium lead, uranium corrected lead ages, and aluminum magnesium systematics in those meteorites. So I think the meteorites need to be carefully assessed for the uranium mineral isotopic composition and possible age disturbances that we have, because right now we have estimates on aluminum-26 heterogeneities within the non-carbonaceous region between the Angrites and Church parent bodies, which probably formed close enough, at least within the NC reservoir. If we add on top of this the chondrules, we have a very limited data sets for aluminum, magnesium, and uranium lead ages. The chondrules also vary across the range of potential aluminum-26 abundances, at least if we think that the systematics are preserved. So going on from that, before finishing, I would like to discuss a bit the dynamical evolution of planetesimals, and what might be important also in terms of chronology. So going back to our ungrouped achondrite, there's also this fascinating ungrouped achondrite that was recovered first as NWA 7325, and since that a lot of paired stones, including 8486, have been recovered, and they formed in very reduced condition. They contain very chromium-rich pyroxene. They're gabbroic meteorites, and they're related in oxygen here, in oxygen isotopic composition, maybe to uralites, or at least the inner solar system. And their ages are also extremely old, within 5 million years after CEIs, at least for crystallization ages from aluminum magnesium. The uranium lead ages are not so precise, unfortunately enough, because of the low uranium content. So when we looked at those, we actually measured the elemental composition of feldspars and pyroxene. This was done by my former student, Paul Frossard, who looked at NWA 8486 and found positive anomalies for both strontium and europium in the pyroxene. And this was fascinating because the only way to model that would be the NWA 7325, 8486, at least, were byproducts, or at least remelting products of an orthozitic crust, which had already positive strontium and europium anomalies. And that was the only way to form, or at least preserve those anomalies by partial melting. So we suggested that probably there were some magma ocean differentiation on the parent body of those meteorites, and an early crust formation by plagioclase flotation that could be possible, and we modeled this as a possibility. And this crust will be reprocessed through melting and forming finally the source of those meteorites by a melting of an orthozitic crust. But something that we didn't found, at least when we look in the collection of meteorites we have, the only anorthositic crust we had so far were lunar. There was no evidence of asteroidal meteorites. And that's something that has now changed. There was some reports last year of the first anorthosites that were actually found in Northwest Africa, first with 15118, but also Van Vazatin 001, potentially related to it. Which have more than 90% plagioclase, or a bit less, but and orthopyroxene. So those 2 meteorites at least could be related from their oxygen isotopic composition and chromium isotopic composition to the HED of Vesta or Vesta-like parent body, let's say. And this was also proposed that there was a plagioclase flotation crust on 4 Vesta to explain their formation. So this is also something that is extremely surprising. If we could form them like this, at least for 4 Vesta, we have no observation. So the crust, the anorthositic crust, will have to be completely eroded. So before finishing, I would like to mention some other work we had done related to this. We also measured with former students, we looked at neodymium isotopic anomalies. So here the stable isotopes of neodymium, the mass-independent variations, also can be looked at as a tracer independently from the radiogenic signatures. And we found that the non-carbonaceous achondrites had a systematic excess in our process, actually, which is always higher than in the non-carbonaceous astatite or ordinary chondrites here, or the 2E iron magmatic inclusions that we measured. And compared to Mars, Earth, and the Moon, that had no isotopic anomalies either by definition for us, but also for Martian meteorites and lunar samples. So what did we obtain from that is, again, the importance of time here, that the non-carbonaceous chondrite sampled an early reservoir that was distinct in nucleosynthetic anomalies. So it was not just related to the location in the disk where those materials found, and we actually found that the carbonaceous achondrites, had the same anomalies as at the NC achondrites, but there was no variation in the outer solar system. There was only variation in the inner solar system with time. And potentially we could see that it could be associated in time maybe with the formation of at least a cutoff here with the formation of chondrites, so maybe the peak formation of chondrules in the inner solar system. So this had to be associated with the thermal event reprocessing the carriers of those isotopic anomalies between the formation of the parent bodies of NCA chondrites and the chondrites themselves. And for Earth formation, it was important because the fact that the Earth is at 0 meant that it could be either formed from astatite chondrites that had very similar isotopic anomalies, or it could be formed from NCA chondrites and a reservoir that would be negative in 148 neodymium, and potentially a contribution of achondrites to the formation of the Earth, which will also affect its elemental composition, but possibly. So from that, we actually used the nucleosynthetic anomalies we measured in the achondrites here, again in green. Those are the group averages for angrites and eucrites. Those are individual measurements, less precise for several ungrouped achondrites. But what we found is that when we correct the nucleosynthetic anomalies for the NC chondrites, the Earth mantle is now non-chondritic and 142 neodymium, so we have a gap. And this has to be explained by early fractionation effect from samarium neodymium ratios. So producing a low samarium neodymium reservoir and a high residual high samarium neodymium reservoir, and the Earth mantle will be enriched in 142 neodymium. So we proposed that collision or erosion was a mechanism to remove this early crust formed, such as an orthositic crust, and would explain the gap we have in 142 neodymium, not only for the Earth, but also for some achondrites or planetesimals. And the removal of those early formed crusts could be 1 to 4% for the Earth, but up to 20% potentially to explain the composition of achondrites. So that was an important result that we published also in 2020. So I would summarize here what I covered. You could follow me. We looked at ungrouped achondrites to expand the sampling of the early formed planetesimal and the crust diversity that has been formed on planetesimals. XH002 was its parent body formed extremely early and with a small radius, probably 20 to 30 kilometers. At least that's how we could model the chronology that we obtained from nature so far. And an early magmatism within 2 million years of sea ice, so before the formation of most of the chondrules and chondrites. So additional studies of achondrites with detailed uranium isotopic composition are needed to assess the distribution of aluminum-26 and the formation age of the solar system. And we also observed indirect, but also direct evidence now of an orthositic crust to have formed on planetesimals. The question now is, could they be linked to magma ocean differentiation by flotation, or maybe some magmatic differentiation? This is going to have to be also assessed now in terms of petrogenesis. The Earth building blocks could be a mixture of chondritic, but also achondritic component according to the nucleosynthetic anomalies. And the excess in 142 neodymium chondrites and the Earth mantle compared to non-carbonaceous chondrites support at least a collisional erosion, dynamical evolution as an important mechanism during the early stages of planetary formation. So I will stop here. Thank you very much for your attention, and I'm happy to take questions. I will give it to Ian now.
Thank you very much, Audrey. That was a real tour de force. You covered so much in terms of what was going on in that critical period before the chondrites appeared on the scene. When we are really trying to see through a fog of melting, if you like, to see what was going on in terms of the accretion time. I thoroughly enjoyed it. So thank you very much. And I'm sure I'm speaking on behalf of everyone who joined the meeting to say it was wonderful. So very well done.
Thank you.
So, I think the chat box has been open for a couple of minutes, and I see there's a couple of questions appearing in it there. So we'll hit a start. And see what. I don't know. It's probably, shall I read it out? The first question is from Stephen Desch. Lots of great info, Audrey, but can we really use ErgChech to test heterogeneity or assess chronometry? As we show in Desch et al. 2023b, all 14 plus achondrites, not just angrites, are concordant and demand T0, what's that, 4568.4. On the other hand, ErgChech was multiple conflicting aluminium magnesium isochrons, multiple conflicting manganese chrome isochrons, multiple lead ages, many of these with disqualifying MSWDs. How can you say you know when ErgChech 002 formed?
Well, I think it's the point I want to make is that we have the chance of having 3 reports for ErgChech, which was not the case for angrites so rarely. And in fact, when there were some issues with dating Sahara 99555, for instance, when different studies suggested different ages, it took a long time to actually reassess those measurements. I think we have also more constraints for ErgChech because now we measure the paroxene and bulk rock, which was not the case for any of the angrites. And we showed that we could have an age gap of 0.6 million years from just using the bulk rock versus the paroxene uranium isotopic composition for ErgChech. So I think it could be the case for angrites. We have to look into that. There's been report of uranium isotopic fractionation between minerals like phosphates or the leached or rock. A lot of those meteorites are also desert. All of them, beside Angrados race, but all of them on this figure are desert meteorites or finds at least. So weathering is also an issue, and we have to be careful with this, I think. Another thing that I wanted to point out, maybe I went a bit fast on this, but the carbonaceous achondrites that we do have measurement for, NWA6704 and 2976, they're actually more consistent with ErgChech than the achondrite anchor. So at least between the inner solar system and outer solar system, we show some a better correlation with ErgChech by taking the average. And I would also point out that the 2 studies by Reger et al. And Koneni et al. Are consistent in the leaded isotopic measurements, where Christian Inoff might have some distinct contribution from common lead components. So I think there could be a lot of discussion on that and reassessment of some of other achondrites. But I think we cannot ignore them.
Yep. Okay, I'll move on to the next question in the chat box, which is thanks for the nice talk. Sorry, this is from Joshua Pakula. Sorry if I've not pronounced that wrongly. Thanks for the nice talk. Regarding the usage for short-lived isotope systems for terrestrial rocks, there is often debate if calculated ages really depict ages or perhaps isotope mixing, e.g. for differentiation ages of 146, 142 samarium neodymium. Is that something you need to consider when working with extinct isotope systems on meteorites or perhaps lunar material? Whole rock, e.g. for dating, or are rather mineral aliquots used for the magnesium aluminium isochrons you showed?
I'm not sure I understood the question. Sorry.
Yeah. Look, We'll come back to that if there's some time at the end and move on to the next question because it's quite short.
I think for the 146, 142 neodymium, here we're not discussing chronology, but we're going back in time and modeling it all at the source, or at least for common samarium neodymium ratio. So going back to a chondritic ratio. And if we do that, and also something I should point out, for the 148 neodymium anomalies, we do not have any effect from hydrogenic contribution. So this is just looking at the distribution of nucleosynthetic anomalies, okay? So I'm not sure I understand the question about mixing. Yeah. So of course, mixing is also always, for sure, if we're producing a mixing line, it's always an issue to interpret an isochron. So we have to assess the contribution of the different minerals and see if there's a correlation with the concentration in the parent isotope, for instance. So this can be evaluated by just looking at the concentration of the parent isotope. So I'm not sure I understand.
Okay, well, we'll move on to.
But we're not using, we're not using, I see the question. We're actually trying to separate mineral phases when we do our mineral isochrons too, and not use mixed fractions,
yeah,
as much as we can.
Okay, so Quinju Yin is asking, what is the uranium lead age differences caused by using bulk versus pyroxene uranium isotopic compositions?
When we did our work, we showed that it's 0.6 million years plus or minus 0.3 million years. And between the study by Reger et al. And Connelly et al., the lead isochrons are consistent, and the difference with our bulk rock analysis a bit lower, maybe due to the leaching method, but this will be less than 0.5 million years we can see on the here. So this difference between the 2 points, the square and the red points, are only due here to the uranium isotopic composition. The red isochrons are consistent for the pyroxene in the report from Connelly et al. So it's still important when we compare to the half-life of aluminum-26, that is 0.7 million years. That's why that when we have estimates of 50% of the abundance of aluminum-26 to 30%, it can be quickly, due to the gap that we have in uranium lead ages.
Okay, I hope that answers your question, Quinju. So here's the next question, Jackbox. Thanks for the wonderful presentation. Have you looked at mass-dependent isotope variations in ERG-Check 002 from volatile element perspective?
I haven't looked myself. I hope people are doing this. That would be really important, yes. We only looked at, for now, ourselves at refractory elements, so like for magnesium, of course, but there's no, I think, report yet for volatile elements, at least I'm not aware. If there are, I'll be interested to hear about it. Yeah, there's the potassium calcium age also has been reported, but again, it's for calcium isotopes and it's similar to the solar system formation age. So there was no, I don't think I've seen any report for that.
Okay, Steve Desch has returned with a follow-up, not a question. The paper Desch et al. In 2023 included CCA chondrites, NWA 6704 and NWA 2796. And they're concordant too, once you account for the isotopic fractionation of uranium during magmatic fractionation.
It makes but this is again very systematic way of correcting ages without measuring the uranium isotopic composition. If you assume just that there's a 0.2 million year gap between pyroxene and bulk rock, we just show that it's wrong for Eggchurch, that we have a difference of 0.6 million years between pyroxene and bulk rock. Yeah. So the uranium isotopic composition has to be measured in the minerals we're using for the leaded isochron.
Okay.
Here I'm just redrawing the figure from Christianinov et al. I want to say. I'm not trying more changes in the calculation of the uranium lead ages that will be arbitrary, I think.
That's what all that's in the chat box at the moment, but I have a little question that I haven't typed there. And that concerns the age of 4, 5, 6, 7.8. That has to be right. It's so beautiful. It was already nice when it was 4, 5, 6, 7. I don't know. I'm just being
this is something that we've been debating for a long time now.
It's just a nice number to have all the digits incrementing by 1 as you go through from 4. but I was going to ask a more serious question. This concerns the size of these bodies that melted at this early stage. Ed and myself have just published a paper which argues that bodies were around maybe just 3 million years after the beginning, which were moon-sized. And I'm just wondering if you have looked at all at just how big some of these bodies might have been very early on. You got any evidence?
Well, I think the evidence we have also is for Mars, from the Martian meteorites. Hafnium tungsten and iron nickel ages constrain, I think, more than 60% of the mass of Mars to be accreted within 5 million years. So Mars is a good example for that.
Yeah.
The other planetesimals, of course, they could have been disrupted. So beside in the asteroid belt so far, beside for Vesta, for which we have a large asteroid, not as big as the moon, but the others have been disrupted, and we have only small pieces left. So it's something that we have to elucidate about what happened to those planetesimals, and is it possible dynamically to have so many large impact events? How did they contribute to the terrestrial planets? So, yeah, that's a big question. Yeah.
Yes. Well, thankfully, there are lots of big questions still there. Otherwise, we'd all have to pack up and go home. Life would be very dull. So, look, we've reached 8 o'clock. We've been going for an hour. So I'll draw the event to an end. Thank you all for joining. Sorry that some of you are probably in the middle of the night. I hope not. But thank you again, Audrey, for this beautiful pull together of the hitherto not completely solved issue of
we have lots to do. That's great.
Concordance among the different chronometers. So thank you very much.
You're welcome. Thank you very much for organizing the lecture series for Ed and inviting me today.
You're very welcome. Right.